Hello, my name is Dillon Mayhew. I work in the School of Mathematics and Statistics at Victoria University of Wellington here in New Zealand. And today I'd like to talk to you about some elementary ideas in probability and statistics. And in particular, how ideas in probability and statistics can be used in the criminal justice system, and how on occasion elementary errors in probability have led to unsafe results in criminal justice. There won't be any advanced mathematics in this talk, just a little bit of elementary arithmetic, some multiplication and some division. So let's begin. Probability is a branch of mathematics, and it gives us a way to quantify likelihood of events. An event is just a thing that may or may not happen, and when we talk about the probability of that event, we are trying to quantify the likelihood that it will happen. We do so by assigning a probability to that event, which is just a number between 0 and 1. Larger numbers correspond to a greater likelihood that the event will occur. And one small piece of notation, if x is representing an event, then I am going to write PR of x to represent the probability that that event will occur. So PR of x will be a number between 0 and 1 expressing the likelihood that x will occur. So for example, if I flip two coins, then I would write PR of 2 tails to represent the likelihood that both of those coins are going to land tails up. So what is that probability? What is the probability of getting 2 tails? Well, there are 4 possible outcomes in this experiment. The first coin could land heads up or tails up, and the second coin could land heads up or tails up, making for 4 possible outcomes, and all 4 of those outcomes are equally likely because the coins are fair coins. So I'm interested in exactly 1 out of those 4 outcomes, so I would say that the probability of my event, 2 tails, is 1 out of 4, or 1/4, or 0.25. People have been thinking about probability for a couple of centuries now, and in the history of this branch of mathematics, they have developed 2 major interpretations of the probability of an event. The first interpretation is called the objective or the frequentist interpretation, and it's probably the interpretation that is most familiar to us from school level mathematics. In this interpretation, the probability of an event says something about the frequency with which that event occurs if we perform the experiment over and over again. So for example, let's assume that we're rolling 2 dice and we would like to know the probability that we will roll 2 sixes. We repeat the experiment by rolling the dice over and over again. And we will notice eventually that the frequency of rolling 2 sixes gets closer and closer to 1 out of every 36 experiments. So in the objective interpretation, we will eventually conclude that the probability of rolling 2 sixes is 1 out of 36, or 1 over 36, which is approximately 0.028. The objective interpretation is the interpretation that we are more familiar with from school, and sometimes this can lead to confusion. How are we supposed to assign probability to an event which can only occur once? How are we supposed to assign a probability when we are not able to run the experiment over and over again? So for example, here is a tweet which is expressing skepticism about the idea of assigning a probability to the outcome of an election, the 2012 presidential election in the United States. We are not able to repeat that experiment over and over again, so how can we assign a probability to the outcome? This is the context where we need the subjective interpretation of probability, sometimes also known as the Bayesian interpretation. And in this interpretation, the probability of an event expresses our own personal confidence that the event will occur based on our subjective analysis of the evidence. And equivalently, the probability of an event in the subjective interpretation expresses how surprised we would be if that event did or did not occur. So when I say that the probability of x occurring is equal to 0, it means that I am certain that x will not occur. And if I say that the probability of x is 1, that means that I am certain that x will occur. If I had a very low but non-zero probability, such as 0.01, that means I would be extremely surprised if the event x occurred. And if I had a very high probability, but slightly less than 1, say 0.99, then I would be very surprised if the event x did not occur. A probability of 1/2, 0.5, means that I don't have any confidence either way. I wouldn't be surprised if x occurred, and I wouldn't be surprised if it didn't. A probability of 0.167 is about the same as a probability of 1 divided by 6, or 1 in 6. So if I assign that probability to x, it means that I would be about as surprised by x occurring as I would be by rolling a 6 on a fair die. A probability of 0.875 is a probability of 7/8. So I can get some intuition for what that means by thinking about flipping 3 coins. When I flip 3 coins, there are 8 possible outcomes, all of them equally likely. So if I assign a probability of 0.875 to the event x, it means that I'm quite confident it is going to occur, about the same level of confidence that I have when I flip 3 coins and I say, I expect something other than 3 tails. So one of the other 7 outcomes. In the subjective interpretation, it's quite legitimate to talk about the probability of one-off events, such as the outcome of an election. So let's think about a recent example. An electoral forecaster might say that Hillary Clinton has a probability of 0.75 of winning the US presidential election. And what this means is that the forecaster has analysed historical polls from previous elections and developed a model for how much predictive power they have about future elections. The forecaster has then looked at current polls and developed a level of confidence that Clinton will win the election. So suppose that this forecaster had developed a probability of 0.75 of Hillary Clinton winning the US presidential election. How surprised would they have been by the fact that she lost? Well, the answer is not actually very surprised. A probability of 0.75 doesn't express very much confidence. It expresses a confidence that she's a favourite, but not that she's an overwhelming favourite. That forecaster would have been about as surprised by Clinton's loss as they would have been by seeing 2 tails come up if they flipped 2 coins. In other words, not very surprised at all. The subjective interpretation of probability is much more likely to be the interpretation we encounter in the criminal justice system. So, for example, a forensic examiner might be looking at DNA evidence from a crime scene, and they might develop a confidence level of 0.999 that evidence came from a particular person, the defendant. And that likelihood, that probability, would be based on their own subjective model of how DNA analysis works and the strength of the current evidence. And with that level of confidence, the examiner would be extremely surprised if it later turned out that the DNA evidence had come from another person. Next, we need to talk about a very important definition in probability. We say that 2 events are independent or independent of each other if the occurrence of one of them has no impact on the occurrence of the other. We might think of flipping 2 coins. The outcome of one coin flip has absolutely no impact on the outcome of the other flip. So now we arrive at this very important equation. If x and y are 2 events and they are independent of each other, then the probability that both will occur is obtained by simply taking the probability that x will occur and multiplying it by the probability of y occurring. For example, let's imagine that we are rolling a fair die and that we are flipping a fair coin. Now the outcomes of these 2 experiments are completely independent of each other. The outcome from the die roll has no impact on the coin flip and vice versa. The probability that we will get a 6 on the die is 1/6, and the probability that we will get a head on the coin flip is 1/2, 1/2. So to find the probability that both will occur, we simply multiply those two probabilities and we get 1/12. It's useful to think of an example of two events which are not independent of each other. So let's imagine that we are rolling one red die and one blue die, and we will let x stand for the event that the total sum shown by the two dice is 11. So what is the probability of x? There are 36 possible outcomes of this experiment because there are 6 ways that the red die can land and there are 6 ways that the blue die can land. All 36 outcomes are equally likely, and exactly 2 of the outcomes correspond to the event x. The red die could roll 6 and the blue die could roll 5, or the other way around. So the probability of x occurring is 2 out of 36, or 1 divided by 18. Now let's consider another event. Let's let y stand for the event that the red die rolls a 6. And it's very easy to see that there are 6 possible outcomes from the red die, and only one of them corresponds to the event y, so the probability of y is 1 divided by 6. So what about the probability that both x and y occur, so that the total on the two dice is 11 and the red die has rolled a 6? Out of the 36 possible outcomes, only one of them corresponds to that event, that both x and y occur, namely, the red die must roll 6 and the blue die must roll 5. So the probability of both x and y occurring is 1 out of 36, 1 divided by 36. On the other hand, if we multiply together the probability of x with the probability of y, then we get 1 divided by 18 times 1 divided by 6, and this gives us 1 divided by 108, which is different from the probability of both x and y occurring. So from this, we conclude that x and y are not independent events. Here is a very well-known example of mistaken thinking about independence. Imagine that a gambler is betting on the outcome of a sequence of coin flips, and the gambler observes that there has been a sequence of 9 tails, and subsequently reasons, well, we are due for a head. There has been a long sequence of tails, and so it is more likely that the next flip will give a head, and therefore I can increase my chances of winning by betting that way. Perhaps at this point you'd like to pause the video for a minute and just think for a while about the root cause of the gambler's fallacy. Of course, the gambler is incorrect. The coin has no memory. It does not know that it's just flipped 9 tails in a row. So it is just as likely to land heads up as it is to land tails up on the 10th flip. The gambler was mistakenly thinking that the 10th flip is dependent on the previous 9 flips, when in fact these are independent events. A little later on, we're going to see a different type of error where dependent events are mistaken for independent events. The notion of conditional probability is closely related to the notion of independence. If x and y are 2 events, then I write PR x vertical bar y to talk about the conditional probability that x occurs given that y occurs. So if I know that y has occurred, what is the probability of x occurring given that extra information? There is a simple formula which lets us find conditional probabilities. To find the conditional probability of x occurring given that y has occurred, we take the probability of both x and y occurring and we divide by the probability of y. So let's consider the previous example again. We're rolling a red die and a blue die, and x stands for the event that the total on the 2 dice is 11, whereas y stands for the event that the red die rolls a 6. Let's find the probability of x occurring given that y has occurred. In other words, we are interested in finding the probability that the total on the 2 dice is 11 given that the red die has rolled a 6. The formula for conditional probability is equal to the probability of both x and y occurring divided by the probability of y occurring. We have already established that the probability of both x and y occurring is 1 divided by 36, because there are 36 possible outcomes, and only one of those outcomes corresponds to both x and y occurring. The red die must roll 6 and the blue die must roll 5. To find the conditional probability, we take that probability of 1 over 36 and we divide it by the probability of y, that is, the probability of the red die rolling 6. So we divide 1 over 36 by 1 over 6. That gives us a conditional probability of 1 divided by 6, or approximately 0.167. And note that we've already found that the probability of x occurring without any condition on y is 1 divided by 18. That number is 3 times smaller, so by applying the condition that the red die must roll 6, we triple the chances of getting a total of 11. Now let's think about what the conditional probability means when we have independent events. So let's consider the probability that x occurs given that y occurs, assuming that x and y are independent events. The formula tells us that this probability is given by the probability of both x and y occurring divided by the probability of y. But we are assuming that x and y are independent events, so that means that the probability of both x and y occurring is equal to the probability of x occurring multiplied by the probability of y occurring. And then we divide that by the probability of y. The probability of y on the top of this fraction is cancelled out by the probability of y on the bottom of the fraction. So we are just left with the probability of x. What we have just established with that argument is that if x and y are independent events, then the probability of x does not change when we apply the condition that y must occur. Conditional probabilities are famous for being counterintuitive. Here's a well-known example. Suppose that we flip 2 coins, and I ask, what is the probability that we flip 2 heads if we are given the information that at least one of the coins has come up with a head? I'll give you another opportunity to pause this video and have a discussion about your answer to this problem. Most people would answer this question with a probability of 1/2. They would reason like so. We know that at least one of the probability that the other coin will come up heads is 1/2. So the probability of getting 2 heads is 1/2. So those people would be surprised to hear that the actual answer is a probability of 1/3. If we know that at least one of the coins has come up heads, the probability that both will be heads is 1/3. Let's see if we can find out why. Let's let x be the event that both coins come up heads, and let's let y be the event that at least one of the 2 coins comes up heads. We are trying to find the conditional probability that x occurs given that y is stipulated to occur. So the probability that 2 heads will occur given that at least 1 head occurs. The formula tells us that this probability is given by the probability of both x and y occurring divided by the probability of y occurring. So let's think about those 2 probabilities. The probability of x and y occurring. Well, the only outcome that satisfies both x and y is if we flip 2 heads. X is the event that 2 heads come up, y is the event that at least 1 comes up. The only outcome that satisfies both of those conditions is if we get 2 heads. What is the probability of flipping 2 heads? There are 4 possible outcomes. We are interested in 1. So the probability on the top of this fraction is 1/4, 1 divided by 4. What about the probability of y occurring? So the probability that there is at least one head. Well, there are 4 possible outcomes: head tails, tail heads, tail tail, heads heads. The only one we are not interested in when we are considering the probability of y is the probability that there will be 2 tails. So there are 3 outcomes that satisfy event y. That means that the probability of y occurring is 3 over 4, 3/4. When you divide 1/4 by 3/4, the result is 1/3. So we arrive at a probability of 1/3. There's another way to explain why this happens. Let's consider all 4 of the outcomes. Head head, head tail, tail head, and tail tail. Now when we condition on the fact that at least one head has come up, we are throwing away one of those 4 outcomes. So we are now only interested in the outcomes within this space. We are picking one of those 3 outcomes at random, and we are asking what is the probability that it will be this outcome, the outcome of 2 heads. When we think about it that way, it becomes clear that the probability of drawing 2 heads from within this constricted space is 1 over 3. One of the key points of this discussion is that confusion about conditional probabilities is very common and potentially very serious, as we're going to see later on. In particular, confusing the conditional probability of x given y for the conditional probability of y given x happens over and over again. Let's consider an example. In this scenario, a murder has been committed on a completely isolated island. There are 1,000 remaining inhabitants on the island, and exactly one of these inhabitants must be the guilty party. We also have some forensic evidence because blood was found on the scene of the murder, and it must belong to the murderer. Fortunately for the investigating bodies, the blood belongs to a rather rare blood group. In fact, only 1 out of every 100 inhabitants is going to belong to that blood group. The police on the island randomly choose an inhabitant, let's call him Mr. Jones, and they test his blood. They discover that it belongs to this rather rare blood group, and so they declare the odds of a random individual belonging to this blood group is only 1 in 100, therefore the chance of Mr. Jones being innocent is vanishingly small, so we are confident of the guilt of Mr. Jones. I will again give you an opportunity to pause this video so that you can discuss this argument being made by the police. The argument being made by the police actually gets made quite frequently, and it sounds convincing, but there are some serious problems with it. Let's see if we can understand why using the tools of conditional probability. Let's let B stand for the event that Mr. Jones, the randomly chosen individual, matches the blood found at the crime scene. There are 1,000 inhabitants on the island, and 1% of them will belong to that same blood group, so we expect there to be 10 inhabitants who match the blood group, 9 of whom are innocent, and 1 of whom is guilty. Let's let I stand for the event that Mr. Jones is innocent. The very low probability that the police are talking about is the probability of B given I, that is, the probability that Mr. Jones matches the blood evidence given that he is innocent. To see why that's true, we calculate the probability of B given I using the formula. So we take the probability of both B and I occurring, and we divide by the probability of I. To find the probability of both B and I occurring, we need to consider the probability that a randomly chosen individual is going to be both innocent but belonging to the same blood group. There are 9 individuals in the island who are innocent but match the blood group, so the probability of choosing one of them at random is 9 out of 1,000. On the other hand, the probability that a randomly chosen individual will be innocent is 999 out of 1,000, because there are 999 innocent individuals on the island. So now the conditional probability of B given I is 9 over 1000 divided by 999 over 1000. And that's equal to 9 over 999, or almost exactly 1 in 100. So the probability that the police quoted in their statement of 1 in 100 is really the probability that Mr. Jones belongs to the given blood group, given that he is innocent. But of course, that probability is not the one we need to consider if we are going to convict him. If we're going to convict Mr. Jones, then we need to be convinced that the probability of his innocence is low. In that case, the probability that he is guilty is high, and we can convict with confidence. So to convict Mr. Jones, we need to know that there is a low probability of his innocence given the evidence, whereas the police have presented us with the low probability of the evidence given his innocence. So the police have confused the two conditional probabilities. So what really is the probability of Mr. Jones's innocence given the available evidence? Well, we can again use the formula for conditional probabilities. We take the probability of both I and B occurring and we divide by the probability of B. We have already established that the probability of both I and B occurring is 9 out of 1000. The probability of B occurring is the probability that a randomly chosen person will match the blood group, and that probability is 1 in 100. So the conditional probability of innocence given the evidence is 9 out of 1000 divided by 1 out of 100, and that is equal to 9 over 10, or 0.9. So in fact, we would have been wrong to convict Mr. Jones because the probability of his innocence is quite high, 0.9. What has really happened here is that there are 10 people on the island who matched the blood group, and effectively the police have just chosen one of those 10 at random. Now 9 out of those 10 people are innocent, so with probability 9 over 10, the police have chosen the wrong person. In that hypothetical example, the police were making a false assumption. They assumed that if there is a low probability of the evidence matching the suspect given the suspect's innocence, then it must follow that there is a low probability of their innocence given the available evidence. But as we've just seen, the first probability can be quite low, while the second probability is quite high, so this is a false assumption. We sometimes call this mistaken belief the prosecutor's fallacy. So now I'm going to lead you through some simple arithmetic. I'm not telling you exactly what we're aiming for, we're just going to try performing a few steps of algebra and we can see where we end up. So we start with the conditional probability of x assuming y, the conditional probability of x given y, and we're multiplying by this ratio of the probability of y divided by the probability of x. So let's see what this is equal to. By the formula for conditional probability, I know that this is equal to the probability of both x and y occurring divided by the probability of y. And I am multiplying that by the ratio probability of y occurring divided by the probability of x occurring. The top part of this fraction will cancel out the bottom part of this fraction, so we are left with the probability of x and y occurring divided by the probability of x occurring. And of course, this looks familiar. This is exactly the formula for the probability of y occurring given that x has occurred. So what we have discovered here is a way of deducing the probability of y given x, starting from the probability of x given y. We must multiply by this ratio of the probability of y over the probability of x. In fact, we have just discovered something called Bayes' theorem after the Reverend Thomas Bayes. And Bayes' theorem gives us a way of converting between the two conditional probabilities. the probability of x given y and the probability of y given x. So let's go back to that previous example and apply Bayes' theorem to it. The police have given us the probability of B given I. That's the probability of the evidence matching given the innocence of the suspect. And that probability is a low probability of 9 out of 999. We would like to know the other conditional probability, the probability of innocence given the available evidence. So to find that probability, we will use Bayes' theorem. We also know that the probability of a randomly selected individual being innocent is 999 out of 1,000, and that the probability of a randomly selected individual matching the blood group is 1 out of 100. So let's put these ingredients into Bayes' theorem. Bayes' theorem tells us that the conditional probability of I given B is equal to the conditional probability of B given I multiplied by the ratio of the probability of I divided by the probability of B. That's equal to 9 over 999 multiplied by the ratio of 999 over 1,000 divided by 1 over 100. And that turns out to be exactly equal to 9 over 10, just as we had arrived at earlier. Bayes' theorem is one of the most important formulas in probability, but it can be a little difficult to remember it. So next we're going to look at a technique which allows us to get intuition for the same phenomenon while using only very straightforward ideas. So this technique is sometimes called the technique of using natural frequencies. And the basic idea is that we're going to understand Bayes' theorem by dividing up a large population into 4 parts. Let's illustrate the technique by example. Let's say that the police use a blood alcohol test, and that if this test is being applied to a drunk driver, then it will give a positive result with probability 0.99. Equivalently, we are saying that the probability of a positive test, given the condition that the driver is drunk, is 0.99. Now let's imagine that the police have applied the test to a randomly chosen driver and that the test has returned a positive result. What is the probability that this driver is drunk? I will give you the opportunity to think about this for a little while. Researchers have actually asked this question in tests, and those tests show that almost everybody will reply that the probability is 0.99. But that's not correct. That probability is the probability of P given D, the probability of a positive result given a drunk driver. We are trying to find the probability that the driver is drunk given a positive result. The real answer is that we do not yet have enough information to determine that conditional probability of the driver being drunk given a positive test. There are 2 pieces of extra information that we need in order to determine the probability of D given P. First of all, we need to know the probability that the test will return a positive result when applied to a sober person. So let's say that that probability is 0.05. This is the probability of a false positive. We also need to know the proportion of drivers in the population who are drunk. This is known as the base rate proportion, and let's say that that proportion is 1 out of 100, or 0.01. Now we have enough information to apply Bayes' theorem. We could use that theorem to find the probability of D given P. But instead we're going to try a more intuitive approach using the technique of natural frequencies. We're going to consider a large population of drivers. In this case we'll say that large means 10,000. And we are going to divide this population into 4 groups, depending on whether they are sober or drunk, and depending on whether they receive a positive or a negative result from the blood alcohol test. First we ask, how many of this population do we expect to be on the right-hand side of the diagram? That is, how many of the drivers do we expect to be drunk? 1% of drivers are drunk So we expect 1% of the 10,000, that is 100 drivers, to be on the right-hand side of the diagram. That means that the remaining 9,900 drivers in the population will be sober. Next we ask, of the 100 drunk drivers, how many will test positive? The test has a 99% accuracy rate when applied to drunk drivers, so 99 out of those 100 will test positive. Obviously, this means that out of the 100 drunk drivers, one will receive a false negative test. Next, we go to the top left corner of the grid. We ask how many of the 9,900 sober drivers will receive a false positive test. The rate of false positives is 5% or 0.05. So the number of false positives will be 5% of 9,900. That's 495 false positives. And finally, we can fill in the last cell of the grid. It will contain the sober drivers who receive a negative test, and the number of such drivers will be 9,900 minus 495. Now let's return to the question of finding the probability of D given P. This is exactly the probability that we will choose a drunk driver if we randomly choose a driver from the positive half of the grid, the half of the grid that is shaded pink. The number of drivers in the top shaded part of the grid is 495 plus 99, that's 594. Of those 594 drivers, 99 are drunk. So the probability of choosing a drunk driver out of that population of drivers in the top half is 99 divided by 594. That's equal to 1 divided by 6, or approximately 0.167. So instead of having a 0.99 level of confidence that a driver who tests positive is a drunk driver, we can in fact only have a much lower level of 0.167. So what explains this discrepancy? The explanation comes from the fact that the base rate is low. It's only 0.01. And that means that of the population of people who test positive, most of them are testing false positive. If we choose randomly from the people who test positive, we are likely to choose one of them. When asked for the conditional probability of D given P, most people will respond 0.99, although as we've seen, the actual answer is much lower, 0.167. In fact, it's impossible to deduce the probability of D given P from the probability of P given D unless we know something about the base rate. So this type of error is sometimes called the base rate fallacy. The key point to take away from this exercise is that if we have a low base rate, then we will have a high rate of false positives. The sorts of errors in probability that we have been talking about have had some very serious consequences in the criminal justice system. We'll discuss a couple of examples. The first of these examples concerns a Dutch nurse, Lucia de Burke, who was sentenced to life in prison for multiple murders in 2003. And the principal evidence against her was statistical. The Dutch criminal law professor Theo de Hoes suggests that there could have been no conviction without the statistical evidence. What happened was that there was a cluster of unexpected deaths while de Burke was on duty, and an expert witness testified in court that the probability of these deaths occurring by chance while she was on duty was only 1 in 342 million. This probability of 1 in 342 million was interpreted as being the probability of de Burke's innocence. Hopefully by now you can spot the error in that thinking. The prosecution was essentially asserting that because there was an extremely low conditional probability of the deaths occurring given de Burke's innocence, it also followed that there was an extremely low probability of her innocence given the fact that the deaths had occurred. Of course, this is a classic case of the base rate fallacy. The base rate that we must consider in this case is the probability that a randomly chosen nurse is going to be a multiple murderer. obviously that base rate is incredibly low, which means that the probability of a false positive, and therefore an unjust conviction, becomes much, much higher. The Dutch Supreme Court exonerated de Beck in 2010, so in this case there is at least a somewhat positive outcome, but that's not the case with the next example we'll talk about. The case of Sally Clark is probably the most famous example of the misuse of probability in statistics leading to an unsafe conviction. She was a British solicitor whose 2 infant sons died of sudden infant death syndrome, that's SIDS, in 1996 and 1998. She was prosecuted for murdering her 2 sons, and during her trial an expert witness testified that the probability of 2 infant boys dying of SIDS in that household was only 1 in 73 million. And largely on the basis of that statistical evidence, Clark was sentenced to life imprisonment. As you can probably guess, there were some very significant problems with the statistical evidence in the Sally Clark case. The first such problem concerns the figure of 1 in 73 million. The expert witness derived it in the following way. He first of all noted that the probability that an infant boy will die of SIDS in an affluent non-smoking household is 1 in 8,543. Therefore, the probability that both sons will die of SIDS is equal to the probability that the first son will die multiplied by the probability that the second son will die. That's 1 over 8,543 times itself, or approximately 1 over 73 million. I'm sure you can identify the problem with that reasoning. The argument assumes that the 2 deaths are independent events, and that is clearly not a justified assumption. There may be some underlying cause, perhaps genetic, that makes both deaths more likely. That would mean that the 2 events are dependent events. In that case, we would not be justified in finding the probability that both events occur by simply multiplying together the probabilities of the individual events. The other significant problem with this statistical evidence is by now familiar. It's the problem of neglecting the base rate. In this case, we must consider the base rate probability that a randomly chosen person is capable of double infanticide, and obviously that probability is very, very low. This means that the probability of a false positive becomes much, much higher, and therefore the probability of an unsafe conviction becomes much, much higher. The Royal Statistical Society released a statement which pointed out these errors in the evidence, and ultimately this led to Clark being released after 3 years of imprisonment. But there are no positive outcomes in this case because she died of alcohol poisoning only 4 years later. To me, this case illustrates very clearly just how important it is to have a populace that is literate in the use of probability. I'm going to conclude with a list of references that I have used while preparing this talk and that I hope will be of interest to you. The first reference on the list is a practitioner guide prepared by the Royal Statistical Society for people working in the criminal justice system. Thanks very much for watching this lecture. I hope you found it useful. This is my email address up here. If you'd like to get in touch with me to discuss any of the issues we've been talking about, then I'd be very happy to hear from you. Thank you.